Hey, so hello everyone, welcome back. So it's a great pleasure to have with us James Hyde from Copenhagen, and he's going to tell us about finitely generated simple groups of homeomorphisms of R.
Thank you very much, Yash. Is this a clicker or do I need to do this? Okay, well, this is a clicker. The artist before, which button clicks? This button? I'll do those two actually. Yeah, okay. So I should say this is all joint with Yash, and some of it's joint with Cristobal. Okay. Do I need to full screen it? Should it be full screen? Okay. Okay, yeah. So it's all joint with Yash, and some of it's joint with Cristobal. Okay. And first of all, I should say what left ordered. I think this was in an earlier talk, but I'll say it again. So a group admits a left order, or a left order on a group is a total order on the group, such that left multiplication preserves the order. And as was also said in an earlier talk, for countable groups, having a left order is exactly the same as embedding in the group orientation preserving homeomorphisms of the real line. And in 1980, Remtolo asked if there exist finitely generated simple subgroups of Homeo plus R, which is the same as finitely generated simple left orderable groups. And that is the goal of the talk. This is the thing we're trying to go through as examples of these. And at the end, we'll have a finitely presented one as well. Okay, so I want to go back to the middle bullet point and just give a vague explanation of why these two things are equivalent. Okay, so imagine you have a left ordered group and you want to embed in Homeo plus of R. So it's already a totally ordered set. So if we take a sensible embedding of that totally ordered set, the group, into the real line, then it's possible to extend the action on the group of left multiplication to homeomorphisms of the Cantor set. I'm covering up a bit when I say if you embed it in a sensible way, you embed the totally ordered set in a sensible way, and that just works. The other direction, if you want to show subgroups of Homeo, or countable subgroups of Homeo plus of R are left ordered, so it's enough to show that Homeo plus of R admits a left order, and then that just carries over to any subgroups. So you're given two elements of Homeo plus of R. Homeo plus, the plus means orientation preserving. So you're given two elements of Homeo plus of R, and you want to give an order to them. And it's in the wrong order. I should have said, first of all, pick a countable sequence or a sequence of elements of the reals, such that the set in the sequence is dense. But then you're given two elements of Homeo plus of R, and you want to know which one's bigger. So you find the first point in the sequence on which they disagree, and whichever one moves that further right is the bigger homeomorphism. And this works for all pairs of homeomorphisms, and it gives you a total order, and you can, with a bit of thought, you can see it respects the left multiplication. Okay. Okay, so the narrative is Thompson's groups are really useful, just like a hammer to hit constructing examples type problems with. We use Thompson's group a lot, so for that reason, I'm going to define Thompson-like, and it's going to make sense for homeomorphisms of the reals, the unit interval, or the circle. S1 is the circle. My circle has circumference 1. So to be Thompson-like, your homeomorphism and your piecewise linear, with the breakpoint set being discrete, so it's going to be finite if you're the circle or the interval, but it could be infinite to the real line. The breakpoints have to lie out dyadic rationals. The dyadic rationals are setwise stabilized. There's no irrational rotations of the circle, they're not allowed. And all the slopes are powers of 2. So F is just the Thompson-like homeomorphisms of the interval, or orientation preserving still. Everything's orientation. Most things are orientation preserving. Okay, and F is super nice. F has this presentation. 2 generators, 2 relations, and they're really nice relations. We can't go home yet. Even though F is finitely generated and a group of homeomorphisms of the interval, and therefore the real line, it isn't simple because it has a commutator subgroup, which is just the elements that are supported away from the endpoint. I should probably draw an element of F for people that haven't seen that sort of thing. So you have, this is just going to be the graph of an element F. So let's say we map a quarter to a half. And just do a linear. So stretch the first quarter to the first half, then map the middle half to the third quarter, and then just do the identity on the last bit. That's a perfectly reasonable element of F. Support in the first 3 quarters, and it point-wise stabilizes the last quarter. Okay. And I should say that this commutator subgroup is that the elements supported away from the endpoints. So the abelianization homomorphism, effectively you look at the slopes at the endpoints, and you look at the log base 2 of whatever that slope is, and that tells you what the abelianization of a particular element is. Am I going too quickly? Making sense? Do ask me questions. Thompson group T is okay, so T is the Thompson-like homeomorphisms of the circle. So just like F, but for the circle. And T is again finitely generated, in fact, finitely presented. And T is simple. So T is in some ways a little bit nicer than F. More complicated, but it's at least simple. But T has, I'll not go to that yet. T has elements of all order. Certainly has elements of all dyadic orders, because you can just take a dyadic rotation. That it has the other orders a little bit more complicated, but not too difficult. Homeomorphisms of the real line definitely have infinite order. So T definitely doesn't embed in Homeo plus a bar. So T isn't an example we're looking for, but it is useful. And one of the ways it's useful is we can make T bar, which is related to T, as the name suggests. So T bar is the Thompson-like homeomorphisms of the real line that commute with x goes to x plus 1. The periodic Thompson-like homeomorphisms of the real line, and T bar is perfect, but it's not simple because it has x goes to x plus 1 as an element, and that's in the center, so it has non-trivial center. But it is, and it happens to be a non-split central extension of T, and we can think of it as the lift of T. And what do I mean by think of it as the lift of T? So we just take all the homeomorphisms of the real line that commute with x go to x plus 1, not even the Thompson-like ones, just all of them. The commute with x goes to x plus 1, the periodic ones. And this has a homomorphism to Homeo the circle, where if your original homeomorphism sends x to y, real number x to real number y, then its image under this homomorphism should send x mod 1 to y mod 1. Okay? And exactly this translating with x goes to x plus 1 makes that well defined. The x plus 1 must then go to y plus 1. So if you take the pre-image and sort of homomorphism from Homeo the real, or these periodic Homeo the reals to Homeo the circle, and T is in Homeo the circle, and T bar is just the pre-image of T. It's all the things that get mapped into T. Okay. And T bar is super useful because it's perfect, which is a bit like simple, but not quite as good. Okay, so still not got to any examples of actual groups that satisfy what we want. But first of all, I'm going to say, why is it hard to make these kinds of groups? So one reason is David T. Morris showed that if you're amenable and finitely generated and a homeomorphism, group of homeomorphisms of the real line, then you have an epimorphism to the integers. So that's definitely incompatible with being simple. Thurston stability theorem shows that if all elements of your group are continuously differentiable, then again you have and you're finitely generated, then you have an epimorphism again to the integers. So like T, for example, like T has all these breakpoints, but it's conjugate to something which is smooth. This is true, isn't it? Yeah, T is conjugate to something which is smooth. So that's the kind of, so you kind of need to find actions that aren't going to be conjugate to something smooth. We weren't thinking about this when we came up with the examples, but it's sort of why they were hard to come by, or one of the reasons. Okay, and then also, if you have some non-identity element which has compact support, when I say compact support, I mean support contained in a compact set. The support's open, so it's not going to be compact, but support contained in a compact set, then the whole group must actually be compactly supported. I mean, support contained in some compact set. But then why not just renormalize the homeomorphism from your compact support back to the real line and use that in the first place? So we can kind of assume that these aren't compactly supported elements. But I should probably argue why this is true. So imagine you have some element with compact support. It isn't true. I need the assumption that G is simple as well. You just said that G is simple. if G simple and has some element with compact support, then you can look at the set of conjugates of that element, but that, because with this simplicity assumption, that must generate the whole group. There's a nice fact about groups, which if you have a finitely generated group and a generating set, then some finite subset of your generating set is a generating set for the group. You don't always restrict generating sets of finitely generated groups down to finite generating sets. Then there must be a finite set of conjugates of your compactly supported element that generate the group, but then the support of the group must just be the union of their supports. But again, that's contained in some compact set. Okay, but somehow these things are all really saying that the real line isn't compact. So, or the interval, the open interval isn't compact. So like you can always have look at what's happening at the endpoints, and that somehow gives you a homomorphism. And we need that homomorphism to be an isomorphism. So we need somehow have some kind of periodicity or something like periodicity that means just looking at a neighborhood near the end tells you all the information about a group element. Okay. We're nearly at the first example. Before we get to the first example, I'm going to do some setup. Okay, so we write half sides instead of half integers. So just A inverse A, B, B inverse B will be our alphabets, but these look like group elements, and I'm going to treat them a little bit like group elements, but they're not group elements. I'm going to kind of concatenate them a bit and take inverses, but they're definitely not going to be elements of the group that we're eventually building. Like we're never going to see a B followed by a B, for example. So we're always going to alternate A's and B's. Okay. So I want to give an example of what a quasi-periodic labeling is. Okay, so imagine we have these half integers. I can count, I promise. Okay. Okay, so we want to label the integers by A's and B's. Let's say that's A, that's A inverse, and let's say this is also A inverse. And I want to label the non-integer multiples of a half by B's and B inverses. So let's just say this is B and this is B inverse, and that can be B inverse, and this can be B. Okay. When we have to satisfy these two conditions, this is just part of it. Just imagine the dot, dot, dots at the end. I want the set of words. Okay, so I'm also going to abuse notation. And I'm going to talk about this as a labeling, but also going to think about them as words, which just means restrict to some interval and just think about that as a word. So on the set of subwords, which means finite subwords, we close them taking inverses. And when I say inverse, I mean just reverse it and switch the sign of the thing. So A become A inverses. So the inverse of AB is B inverse A inverse. So close the set of subwords should be closed and taking inverses, and whenever you have some subword in there, then there should be some n, so that any word of length n, that's a subword of your labeling, has your original subword as it's somewhere. So if something happens somewhere, then it happens reasonably frequently. It doesn't have to be like in a periodic way, be some kind of intermittent way, but there's some bound on the gaps between them. Okay. I should also give an example. So I'm going to build an example with just an A, and then W1 is supposed to be W0 with an A with B inverse in front of it, B after it, and the inverse of the thing there, and the inverse also here. Then next time I add to the B2, I just write this here, put a B inverse in front of B after, and the inverse of this here, and the inverse of that there. It's not too difficult to see that we're going to satisfy these conditions, because if something's a subword, then it's going to appear in Wn for some Wn, then both it and its inverse are going to appear in Wn plus 1. But then if you imagine the word being written in terms of Wn's and B's, any subword of that that contains a Wn is going to have the original word and its inverse that That's still got bounded length. Okay. But they're not too difficult to come by. Okay, so now we're actually coming to the first example, which is the first example from Yash and myself from 2018. Okay, so imagine we fix one of those quasi-periodic labellings W, and for each element, this is F as in Thompson's group F as in homeomorphisms of the interval that are F-like that we defined at the beginning or earlier. So for each one of those, we're going to define alpha gamma and beta gamma. This is going to turn out to be a homomorphism from F, or pair of homomorphisms from F into Homeo of the reals. Okay. Alpha gamma, okay. Alpha, so imagine that, and I also say gamma bar in there. Okay, so imagine that gamma does something like this. So imagine that's the unit interval, and imagine gamma has support over here, and it moves stuff right on that bit. 0 and that's like 1. And it point-wise stabilizes this stuff and it just moves stuff right there. Okay. Then gamma bar is the conjugate of gamma by the orientation reversing isometry of the unit interval. So it's going to move stuff this way, like that. Just a little the same, but flipped. Okay. So alpha gamma, I'll just draw alpha gamma up here. It should do above an A, it should just do gamma. So on this interval, it should just do this. Above the A inverse, do the opposite. Above the other inverse, it should also do the opposite. So alpha gamma fixes the non-integer multiples of a half. Okay. So it just does gamma or gamma flip, depending on whether it was an A or an A inverse on each interval like that. And beta gamma is much the same, but for the B's and offset. So on this interval, because there's a B here, this is going to be beta gamma. We're going to do that, just like gamma. And because this is a B inverse, we'll do that. And then again, B inverse, so like, and these are homomorphisms. This is just, you're taking F and you're putting it in Homeo of the real line, sometimes flipped, sometimes not. And you look in two different ways, and each of those, each one of those ways, each of those homomorphisms is, or monomorph, including that embedding, is really just an embedding that isn't very complicated, but the way they overlap makes it a bit more complicated. Okay. This is making sense? Yeah. Like it's yeah, it's a homeomorphism, so there's no negative bits. Yeah. Yeah, they're both isomorphisms map into Homeo R. Okay. GW be the group generated by the union of the images of these two monomorphisms. Okay. So, and the theorem, Yash and myself from 2018, that GW is finitely generated and simple. This was the first example of a finitely generated simple right orderable group. Okay. No one has any more questions about that? At about this time, Nicholas Mathibon and Michel Tristino published a paper with another example, which is somehow much more canonical. Like, it's weird that this pathological thing, like, for example, every element of this group, GW has a fixed point somewhere, like lots of fixed points. Because as soon as you have some point that gets moved, you can look at the label around it in some big interval. And then when that label exists somewhere else as an inverse, your point has to be kind of moved the other way there. And then there must be a fixed point between the two. So it's like quite pathological. So their examples were nicer and somehow more Thompson groupy, even more Thompson groupy. But also there was like a paradigm that came with their example that somehow all these things are acting on mapping torus. And that's really nice. I'm sorry, I'm not going to explain it. But you could ask Michel Tristino. I might hint at that. Okay. Okay, so the second example, actually, I think really the second example had been like floating around with Colin Blake, Matt Bryn, Martin Kasselbov, and Justin Moore and Matt Zarimsky for some time. So that actually happened before, but they didn't know that it was, well, it actually isn't simple, but its commutator subgroup is simple, which I'll come to. They didn't know that this, sorry? And finally generated. They hadn't studied the commutator subgroup. Okay, so that's a block of text. I'm going to draw a picture that might make more sense. Okay, so we have, so this is going to act on the circle. We're going to have 3 generators, and the way they overlap is we have one that kind of goes a third of the way around and moves stuff clockwise. Another one that kind of goes goes 2/3 of the way around, and this one does kind of that. So each one moving, so the bits I've drawn is the support of the generator. So each of these lines represents one of the generators, and so this generator here has support. I've not drawn the circle because then it just looks like concentric rings, but imagine there's a circle here. So this line corresponds to a generator, which moves this part of the circle clockwise around there and pointwise stabilizes this bit here. And each of them do that, and they all overlap in this way. So any 2 of them generate a copy of F, but together their behavior is more complicated. And this is a super nice group, and it's not in the fast group stuff, which is just exactly the right word for those things. So one of the things that the fastness gives you is that if you replace a generator by a power, then it stays, you don't change the isomorphism type. We have this picture combinatorially describes the group, so long as this element maps this point to at least somewhere, and this, as long as each one moves points far enough, it's combinatorially determined up to isomorphism just from that picture. Okay, but it embeds in T, but it's somehow less complicated than T. Okay, but in action the circle, the commutator subgroup of fast T, so this time it was with Rivas as well as Lodha, is finitely generated and simple. Okay. But you're saying, wait a minute, this is the circle, not the line. Why is that an example of a finitely generated simple right orderable group? Well, the reason is fast T embeds in Homeo R, and so its commutator subgroup does as well. And this is the fastness. Somehow, if you pick a point and look at its orbit, I'm going too fast, maybe. If we pick a point and look at its orbit, the point sort of never hits itself unless you really undo the same thing again. If you look at the Schreier graph of a point, then it just looks like a tree with loops for points that aren't in the support of the element, but otherwise, at least that's true for reasonably well-chosen points. Okay. Yes, this is true. The lift of the group to the line in the same sense as before was isomorphic to the group cross the integers, because they also have the integer translations. Yeah. So this time the lift splits. Okay. And so one way of defining it, which I don't have these slides, is means a different thing now, is you take your element, you just take the same thing on the real line with the fixed points. Of the lifts, you take the one that has fixed points, generate a group from those, and that's isomorphic to fast T. Okay. Okay, so H bar is also finitely generated and simple. Okay, so this is another really nice example that was also with Cristobal. So what you do is you take Thompson's group T, and rather T bar, and then you stretch it by a factor of lambda. It makes a stretched version of T, which looks a lot like T. And then you take your original copy of T bar, so it takes a lot of stretched version of T bar, looks a lot like T bar, your original copy of T bar, and you're uniting them together, and you generate a group, which doesn't seem very complicated, but it turns out to be finitely generated and simple. But proving that it's finitely generated is super easy because T bar and T bar lambda are both finitely generated. Proving it's perfect is pretty easy because T bar and T bar lambda are both perfect. But proving it's simple required some more work. That was fairly fiddly. So having said that, there was like 20 minutes of great excitement in the sand when we did that. So it was a very dense 20 minutes. Thanks, Colin.
It's really bad.
I mean, it's following the Epstein kind of
It's
ethos.
using that,
Yeah.
But it's not.
Yeah. I mean, you're still trying to get some element to support gets moved off itself, so by some other element, so you can do commutators and do something, but there's a load of other tricks in there. No, like this has translations.
Have elements in one that lambda is irrational. When you compose, then you get something very. That's where all the.
Like it has, just because on some interval it has a tiny bit of support, like it could do other weird, unpleasant things on other intervals.
Is that you kind of come back very close to quasi-periodic.
Yeah, sort of. Yeah. Rational number. Then, yeah, it won't be. Yeah, exactly. Yeah. Fourth example. Okay. G6 is a subgroup of orientation preserving piecewise linear homeomorphisms of the positive reals with slopes powers of 6. Okay. So earlier on, I defined Thompson-like homeomorphisms because I wrote these slides when only the first 3 examples existed. And so I couldn't find a way of using Thompson-like to encompass these examples. So this is a slightly different notion. There's many, many generalizations of Thompson's groups. Okay, so G6, the slopes are now powers of 6. And we're acting on the positive reals. I should also say that this example is due to Yash and myself. This specific action is due to Jim Belk. We had like a more complicated version that acts on the circle and a more complicated version that acts on the line. They conjugate onto the positive reals and it gets much nicer, which is this version. Okay, so it would have infinitely many breakpoints, but they've got to be discrete, and in particular, where they can accumulate but only at 0 and infinity. Okay. So then take the subgroup of those things that commute with x goes to 2x. And remember that 2x goes to 2x is not an element of G6. It has slope of power of 2, and G6, everything has to have slope of power of 6. Okay, and then take the commutator subgroup with that, which happens to also have an action on the circle, and this one is finally presented in simple. It's somehow a lot like T. I spent a long time going, and I'm sure Yash did as well, going through lots of weird examples of complicated things that were much more like the other examples of the apart from fast T, where you have this kind of quasi-periodic and trying to think about ways of encoding things that could maybe end up making something finally presented. And none of it worked. And I thought, but probably there's some way of showing that the fast T-like things, one that act on a circle, probably they can't be finally presented. And then eventually, and we realized that this actually does work, and you do get a finally presented one like this. So it wasn't where we expected to find it.
A cousin of.
Yeah. And it's this is, I think, the first like Thompson-y family group that like all they have like oodles of generalizations of T acting on the circle, and oodles of generalizations of V acting on the Cantor set. And it's a really natural question to ask, okay, what about generalizations that act on the sphere or the torus or something? And we don't have any examples, or at least not finally presented simple ones. Sorry? No, it doesn't. No, there's like an actual minimal action on the circle. Sorry? Yeah, like modular dilation by 2 becomes x goes to x plus 1. on the line and then, yeah, sorry. No, it's definitely too generic. Well, the fast T is 3 generated because it's a billionization of Z cubed. Yeah. So the commutator subgroup of this will be 2 generated. But the commutator subgroup of fast T is 2 generated.
This one is going to be, I don't know.
I mean, I'm hunting for one, but I'm not on the same continent as one. So. Sorry? And the any guesses what the abelianization is? No, the commutator subgroup is simple. Oh no, the abelianization of gamma, subgroup of G6, the things that can move x to 2x, the thing that has Q as its commutator subgroup. You're on the paper, Yash. You can't guess. That's cheating. Sorry, go on. Oh, it's Z to the 5, right? Yeah, Z to the 5. Because each orbit, so G6 has these breakpoints, and the breakpoints all look like something. Well, no, just look at F6. So this has F6, so as in the thing that has F6 on the interval 1 up to 2, and then just does translations of that stretched elsewhere to commute with x goes to 2x. So that has orbits, and the orbits look like something divided by power of 6. And two of those potential breakpoints are in the same orbit if the something is the same mod 5. This n-1 happens a lot in Thompson's groups. And you can look at the log of the slopes on either side and look at the differences of them, and then you can sum that up over a particular orbit of breakpoints in an interval of a fundamental domain of x goes to 2x, and that gives you a number. And the sum over it add to the so you get 6 of these orbits, but the sum of each of the integers you get for each must add up to 0. So you only get z to the 5 in the end. Proving like the paper that did this, like I only did the G6 version here, but we've found infinitely many examples by using slightly different numbers. It got really complicated, somewhat disappointingly given how uncomplicated this is because of all these orbits. Is that a question? Yeah. Yeah.
Generally, just by looking at the creation.
Yeah, I would say that if you want marked isomorphism, as in taking the 2 copies of F from this group to the 2 copies of F from that group, then they're isomorphic exactly if this labeling has the same set of finite subwords as this labeling. I don't think that's not too difficult. But then showing that there aren't other isomorphisms that are weirder, I assume there aren't, but I don't know if we've actually done that. Okay. You did that. Okay. Okay, that makes sense.
If the finite subwords, we proved this in our paper with Rivas and For any finite subword, you can construct an element non-trivial if that finite subword.
But this is the marked isomorphism again.
Yeah. So, but I think that's.
No, I think what you're saying is that the mapping torus that you act on is going to be non-isomorphic exactly if the finite subwords are different, and then apply Rubin. Okay. So it's hard enough that we didn't do it, but not so hard that they didn't do it. I don't know what that tells you. Or maybe we did do it. I can't remember. Oh yeah.
None of them.
No. Yeah.
They're all non-trivial limits. None of them are.
Yeah. I think. So in that case, the mapping torus you get. Maybe we don't have time to describe the map. So there's each of them acts on the torus. Like if you imagine having a torus and having a lamination, and the angle of the lamination is determined by a rational number, and they all preserve this lamination and preserve each leaf of the lamination, and one of them kind of acts such that it does, on one circle it does t, but then it also moves stuff up and down. So it preserves the verticals, and it moves them right and left according to t, and then it moves them up and down and bits them up and down in order to preserve the lamination. Then do the other copy of t bar using its action of t the other way, and this gives you a nice piecewise linear action on the torus. And this is kind of exactly the thing that sort of has to happen from the paradigm that I mentioned earlier from Nicholas Mattibon and Michel Tristino's paper, that whenever you have one of these, there's a mapping torus living in there somewhere. Okay. So for fast t, the mapping torus, and for this one here, the mapping torus is just a circle, just a trivial version. But for the double lift of t, you do get a torus. So the point of what I was saying was that you can't use Rubin then, because it's still just a torus. But maybe, and their torus is homeomorphic, but maybe. Okay. Okay. I was definitely about to solve it, but I held back for the record. So I'm not sure if that answered your question. I talked long enough, you forgot the question. Okay, that's good enough. Any other questions? All of them will have all of them will have maximal abelian subgroups of any rank. Oh no, maximal abelian subgroups. Oh, maximal. Is it, sorry? Yeah. This was a question that Jim Belk and myself and Francesco Matusi answered. But really, Colin and some other people answered it, and then without knowing the question. But then, like Jim and Francesco and myself knew the question and the answer at the same time. Yeah. Oh, okay. I was lucky. Yes. It was something that Igman was interested in, according to Martin Dridson. Not you didn't write it down anywhere, though, I don't think. Yeah, it's in the Crofton notebook, yeah. But it isn't a question, it's like part A of a question. They also want GLNQ. What can that embed in? That embed in something finally presented. Anybody have like a question that would last like 45 seconds? Okay. Thank you.